30 hours. Not sure there. It's so strict. Oh my God, that's absurd.
Okay, how you guys doing? Okay. We finished week 3. We have 13 more to go. 13 or 12? To the end of the semester. I'm counting the end of. Okay, so before we start with a new topic, is there any questions about the homework page?
Yeah, can we go over like the 75?
75?
Yeah.
The box?
Mm-hmm.
Okay. Yeah, that one's kind of.
I think I have it, but I don't.
That one is kind of tricky. So we have a box against the wall, and the mass of the box is 1 kilogram. And I apply a force, and that force is 12 newtons at an angle of 30 degrees. We're going to have a friction, and what we want to find out is if there's any motion, if there's any acceleration on the box. And in what direction? And if there is, in what direction? And what we know, one of the initial conditions that we know about this is that the box is at rest. Okay, so the box is at rest, and what I want to find out is if that force that I'm going to apply, if it's large enough to start, for that book to start moving, and if so, in what direction? Like it can go upwards, it can go downwards, or it can go, or stay still. That's my 3 options. So I have move up, move down, and stay still. Okay. So first thing, I'm going to assume that the box is at rest. So I'm going to assume that the box is not moving, and I want to know if my force is big enough to push it. Okay. So I'm going to do my free body diagram, and I'm going to have, I have the force that I'm pushing. I have the weight of the box pulling down, and I'm going to have a normal force from the wall to the box. So the normal force is going to be pointing, in this case, to the right. So my free body diagram is going to look something like this. So I have the 12 newtons here. This is going to be 30 degrees. I have the normal force, which I have no idea where it is. And I have the weight. Oh, I have the weight. And I'm missing friction. I'll talk about friction. I have the weight. And the weight for this case is going to be 9.8 newtons. In addition to this, I'm going to have friction. And I don't know what direction is going to be friction, because I don't know if it's moving up or it's moving down. So in general, if there is a force or a variable that I don't know where direction is going to be, and I need to make a guess, it is convenient for you to assume that that variable is going to be positive. Okay? So a positive friction force means that it's going to go like this. So you can imagine that the box is actually trying to move down, but the friction force is opposing that. And the only reason that I'm picking that direction is to make my friction positive. That's the only reason. So this is going to be my free body diagram. Now, because I'm assuming that all my forces are, because I'm assuming that the box is standing still, because I'm assuming that the box is static, that implies that all my forces in X are going to be equal to 0, and all my forces in Y are going to be equal to 0. Okay? Oh, I forgot. Another piece of information that I have is that the wall is made out of wood, and the box is also made out of wood. So we have wood on wood. So the static coefficient in this case is 1.5. So this is wood on wood. And this comes from a table in your textbook. So this is my Newton's second law equations. These are the ones I tried to solve. And I'm going to start with the forces in the X direction. And I'm going to have that in the X direction, I have the applied force, the X component of the applied force, plus the normal force. That's going to be equal to 0. The X component of the applied force is going to be negative 12 cosine of 30, plus the normal force is going to be equal to 0. The normal force is 12 times cosine of 30. And this is going to give you 10.4, I think, something like that. 10.4 newtons. Okay, so that's the normal force. Now, in the Y direction, I'm going to have three forces. I'm going to have 12 sine of 30 positive. That's the applied force. I'm going to write that. I'm going to have the applied force in Y plus the friction force plus the weight is going to be equal to 0. Those are the three forces that I have. So I'm going to have 12 sine of 30 plus the friction force, which I don't know what it is, minus 9.8, which is the weight. It's going to be 0. So I'm going to be solving for friction. So I'm going to have that the friction is 12 sine of 30, no, negative 12 times 30 plus 9.8. And this, can someone tell me what you guys got? Anyone?
3.8.
3.9?
Yeah.
3.9. Okay, so that's the friction force that I'm experiencing right now. Now, with this number on its own, I cannot tell if it's moving up or down, or if it's static. What I need to do is to compare this with the maximum friction force. Remember that the static friction force has a range, and as long as that this friction force doesn't exceed this maximum threshold, it means it's going to stay static. So I'm going to have the
Sorry, it's 15.8.
15.8? No.
No, it's minus.
It's negative 12.
God, I'm sorry.
Yeah, this is 6. Yeah, 6. Yeah, so it's going to be 3.9, 3.8.
Yeah, okay. Yeah.
3.8.
So I'm going to calculate the maximum static force, and this is going to be mu s times the normal force. Mu s is 0.5. The normal force is 10.4. So this is going to give me 5.2 newtons. So because the threshold before motion is 5.2, and what I'm experiencing is 3.8, then it means that this box is static. Yeah, makes sense. Ian, you got it? Jacob? Noah, you got it? Over. Action. Paige, you got it?
Yeah, I
Ish?
did it a lot different, so it's a good thing.
Yeah, probably there are other ways to solve it. This is just one. Any other questions? Okay, so we're gonna start with a new topic. We're gonna be talking about. So far, what we've been talking about is that when you apply a force to an object, that object can displace or not, depending on how of the magnitude of the force and the direction of the force. But we've always been talking about one of the consequences of this applying the force as a translation motion. However, that's not the only thing that can happen. If you have an object and you apply a force or two forces, the object can rotate. And we haven't talked about rotation. And one of the reasons that we cannot talk about rotation is because, well, we have a point, object. So in the model that we've been working is that if you have whatever object you want, we change that into a point, and we've been working with that point. So by definition, that point cannot rotate because it has absolute symmetry. You cannot tell if a point is rotating. So what we're going to do now is that we're going to move away from the point model, and we're going to be working with extended objects. So with extended objects, basically we care about the geometry of the object, but what we're going to try to do is to simplify the object that we're going to try to analyze it while trying to respect most of these properties. So what do I mean? Okay, so we have the bird. Now, working with the shape of a bird is a little bit complicated, but I can approximate this bird maybe with a square. And as long as the dimensions of the square are similar to the dimensions of the bird, and as long as the mass remain the same, then I can assume that the square is going to be a model of the bird. And I can apply this to pretty much everything. Like, I don't know. If I have a person, I can kind of represent this person as simple geometric figures. I know this drawing sucks, but you get the idea. Okay, so the idea is that instead of working with the true geometry, we're going to try to simplify it, and then we call this an extended model or an extended object model. And one of the consequences of this is that these extended objects, they can actually rotate. So what we need to analyze is, okay, how do we know if an object is rotating? How do we measure that rotation? Or how do we estimate the force that's causing that rotation? Okay, makes sense? Okay, so these on your book, these are sections 7.3 and 7.4. So we from chapter 7, we're just gonna cover these two sections, and then we're gonna jump to chapter 8. Okay, so the first concept that we need to talk about is called torque. If anyone is into cars, you will have heard torques or the term torques before. Uh, and torque is a specific kind of measurement that we have for rotating objects, and torque is kind of like a force or similar to a force. Okay, the main difference is that a force is going to create a linear displacement. And it can create an acceleration and can create linear velocity. But this, when you apply a force, the idea is that it's always going to be displaced in a straight line. Torque, on the other hand, it creates a rotational displacement or creates a rotation. Yeah, so torque is kind of the equivalent of a force, but torque is specific for objects that rotate. Okay. So a very classic example, let's say that you have a person and you have the arm, the shoulder, the elbow, and the hand. So you have the shoulder, the elbow, and the hand, and this is the elbow. Okay. And what we're gonna be looking at is at the torque on the elbow. So we're looking at the torque at the elbow. Okay. And what we're gonna do is that we're gonna apply a force close to the hand. It can be that it's pushing something, or it's catching a ball, or it's being pulled by a rope or something. Okay, but that's the force that is being applied, and we're gonna calculate the torque on the elbow. Now I'm gonna do an extended object on my arm. Okay, you can represent the arm with either a cylinder or a rectangle, or yeah, kind of a rectangular prism. But when you see from the side, it will look like a rectangle. Okay, I'm gonna redraw it a little bit larger. Okay, and here's my elbow. Okay, so you can imagine that when I apply the force, the arm is going to rotate, and it's going to rotate along the elbow. Okay, the elbow is what we call a pivot point. And when we are talking about applying a torque, and when we're thinking about objects rotating, we always need to identify a pivot point, and it's always going to be one. We can choose a pivot point, and sometimes the pivot point is kind of natural. It's actually given by the problem. Like in this case, the elbow is a natural pivot point. The shoulder is a natural pivot point. And actually, in the human body, almost every joint is a kind of a pivot point. So I'm going to have the pivot point, and I'm going to draw an what's called a radial axis. And the radial axis is going to go from my pivot point, and it's going to move along the object that I'm analyzing. Okay, and this is called the radial axis or radial line. Okay, and you can imagine that this force can extend all the way to that radial line. Okay, so here I have a couple of measurements that I can take. One is the distance from the force, from the intersection of the rows of the force with the radial axis, all the way to the pivot point. So I'm gonna look for this distance. Okay, and the other one is gonna be an angle, and I'm gonna have this angle over here, and this angle I'm gonna call it phi. Okay, so the way I calculate the torque is basically going to be a relationship between the distance from the pivot point to the force, the angle, and the magnitude of the force. So the torque is defined with this letter tau, and the torque is going to be the distance r times the force sine of phi. And I'm going to explain why we're working with sine of phi. Mallory, how you doing?
Good.
Okay. 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 So we're going to be working with this. Now, if we look at the units, force is in newtons and distance is in meters. So the units of torque is Newton meter, which is a weird unit, but that's what we use. The force is a vector. Distance is a scalar. So torque has also had to be a vector. Now, in our case, because we are using non-calculus, the directions of the torque is actually quite simple. The torque can only have two directions. It's either clockwise or counterclockwise. So when it's clockwise, we assume that the torque is negative. And when it's counterclockwise, we assume that the torque is going to be positive. Okay, so does it make sense so far? Yeah. Okay, so I'm gonna go and try to explain where does this sine of phi comes from. So I'm gonna redraw this thing over here. So we have my pivot point, I have my line, I have my force, and I have this angle over here. Okay, so the same way that when we have a tilted plane, we change our axis of rotation, our reference, our frame of reference. When we're working with torques, we also gonna have a different frame of reference. And the frame of reference is basically the same two axes. one axis is gonna be along the radial line. So we're gonna have an axis like this. And the other axis is gonna be perpendicular to that one. Now, the one that is parallel to the radial axis, we call it the parallel axis, and it's just two parallel lines. And the perpendicular axis, we call it perpendicular axis. Okay, so instead of calling it x-axis and y-axis, we just call it parallel and perpendicular. And that's because the torque can be applied at any angle. This arm can be like this, or it can be like this. So it's always going to be a parallel and a perpendicular axis. Okay. Now, this force over here, it has two components. I'm gonna redraw the force. So I'm gonna redraw the force over here on this angle. It's gonna be 5. No. This angle is gonna be 5. Now, I hope everybody can see that this force is gonna have two components. It's gonna have a parallel component, and it's gonna have a perpendicular component. Yes?
You can redraw it in a different quadrant.
Just to keep the notation that we have, that we put the beginning of the force at the origin, and then the end. It doesn't really matter as long as I don't change the direction. Just so you can see the direction of the parallel component and the perpendicular component. Now, the parallel component is going to be along the x-axis. Okay, so imagine that you have your arm, and you have your arm extended, and someone is pushing your arm away from you. So that force is not going to rotate your arm with respect to your shoulder. The same way, if you push it forward, it doesn't rotate. Okay, it can stabilize your shoulder, or it can dislocate your shoulder, but it's not going to rotate it. Okay, so the parallel component of the force doesn't rotate, or doesn't cause any rotation. The perpendicular component is the one that causes rotation. So when we calculate torque, the only component that we care is the perpendicular component. So you can say, well, the torque is actually the distance from the pivot point to where I apply the force times the perpendicular component of the force. Now, if you look at this frame of reference, and if this is phi, then the perpendicular component is going to be r times the magnitude of the force, sin of phi. Okay, you have to be careful. Some way that we're working so far. Don't try to memorize this RF sin of phi. Try to think more in terms of the radius times the perpendicular component, and then try to find out what is the perpendicular component. Sometimes it's going to be sin of phi, sometimes it's going to be cosine of phi. And we're going to do a couple of problems so you can get an idea. Okay? Make sense? Any questions so far? Okay. That's one way that we can calculate the torque. Another way that we can calculate the torque is by using what is called a moment of arm. Okay. And I'm gonna do it just in a different configuration. So again, we have our arm with our shoulder. Now I'm gonna have the force going like this. Okay, and this is gonna be my angle phi. This is gonna be my distance. Okay. And instead of trying to find out the perpendicular or parallel component of the force, what I'm gonna do is that this force, I'm gonna extend the force. So I'm gonna imagine, I'm gonna draw an imaginary line that goes in the same direction as the force. So I'm gonna draw something like this. Okay, and then I'm gonna draw a line that goes from the pivot point and is perpendicular to this imaginary line that I just draw. So I'm gonna draw a line, and this angle is gonna be 90 degrees. And if this is phi, then this one is also gonna be phi. Okay, notice that in this configuration, the radius is the hypotenuse of this triangle rectangle that I just draw here. Yeah. So I'm gonna redraw it over here. So I have the hypotenuse, this is R. This is phi, and this is the angle. So now what I'm gonna calculate, the moment of arm is this guy, is the line that goes from the pivot point to the force. So this is the moment arm, which is basically, yeah, this is the moment arm. And the moment arm is basically R sin of phi. And to calculate torque, is the moment arm times the force. So that will be R sin of phi times the force, which is exactly what we had before. Okay, sometimes it's easier to work with angles and try to find out what is the perpendicular and parallel components of the force. Sometimes it's way easier to calculate the moment of arm. And even sometimes just by measurement, you can calculate the moment of arm. And we'll do problems with that. Okay. Any questions so far? Okay. So let's do a simple example. Let's imagine that you have the arm of a person. You have what is the elbow? And I'm gonna say that on your hand, you are holding a dumbbell, and this dumbbell has a mass of 10 kilograms. Right now, I'm gonna ignore the mass of the arm. So you have that. And the distance between your elbow and your the dumbbell, I'm gonna say that that's 45 centimeters. Okay, so calculate the torque. So try to do it on your own. Try to calculate the torque. That's the force that you apply. But if you hold in the 10 kilogram dumbbell, that's going to try to pull your arm down.
How much is it maintaining?
So it will be the weight of the dumbbell that will be your flat force. And it will be 9.8 times 10 kilos. Not yet. Okay. It has to be here. So the gain of torque is okay, so again, what we need to do is to identify all the elements that we need to do to calculate the torque. One of them is the applied force. Now, the applied force, we don't see it here, so the problem doesn't say specifically what is applied force, but the object that we have here, the mass of 10 kilograms, is gonna have a weight, and that weight is gonna go like this. So this is gonna be my applied force. So in this case, I'm gonna have 98 newtons of applied force. The other thing I need to identify is the pivot point. Again, the problem doesn't tell you what is the pivot point, but if it's an elbow, you can imagine that this is gonna be your pivot point. So I know the distance between the pivot point and the normal force. And the last thing, so this 45 centimeters, that's going to be my R. And this is going to be my applied force. Now, the last thing that I need to do is to find out what is the perpendicular force to the radial line. And the radial line is going to go from the pivot point to where the force is being applied. So the radial line is going to go like this. And in this case, this gravity is perpendicular to the radial line. So that's going to be the force, the perpendicular force to the radial line. So the torque is the radius times the perpendicular force. This will be 45 centimeters. We convert it to meters, so it will be 0.45 meters times the force, 9.8, 98. And we get, Aubrey, what you got, 44?
44.1.
44.1 newtons meter. Now, remember, torque has a direction. It's a vector. If it's rotating, if the force is causing a rotation that is clockwise, this is going to be a negative torque. So this torque has to be negative 44.1. And the negative basically means that it's rotating clockwise. Okay, makes sense? We're gonna try to do another one. This is just a piece of wood. And the pivot point is gonna be not at the center, it's gonna be more to one side. And you can imagine that the distance from one side to the other one is gonna be 25 centimeters. And from the other side is gonna be 75 centimeters. This is a 1 meter long piece of wood, and the pivot point is at 1/4 of the length. And we're going to have two forces, one on one edge, and this is going to be 10 newtons, and the other one at the opposite side, and it's going to be 20 newtons. Okay, so I'm going to call this F1, and this is going to be F2. Okay, each one of these forces is going to create its own torque. So the net torque is going to be the sum of the torque created by force 1 plus the torque created by force 2. Okay? So give it a try and try to calculate what is the net torque.
then how do you go to this version versus like when we use videos?
It's the same question, actually. It's just that the angle here is 90 degrees. So sine of 90 is 1.
This one?
No, between the arm and the horse.
Okay, so then what did I do wrong here? So this would be, this would be 45. That's 1.45. And then
So it's r sine of 5 instead. So you put that in 5.
oh, so that would be 90. And
So so we're gonna look at this. So they ignore this force, and this is going to try to rotate clockwise. So that was going to be negative. Whatever we're talking about from there is going to be a negative. And this one is rotating, so that's going to be positive. And then this.
Okay, so really quick. So we have two torques. I'm going to calculate first the torque caused by the first force. So tau 1, and also, by the way, try to get used to write a tau and not a t. Eventually, we're going to be working with periods and time, and we use t for that one, and it gets a little bit confusing. So try to do the tau or a fancy t just to distinguish it from other units. So you have tau 1, and that's going to be the distance, which is going to be 0.75 times the force, which in this case is 10 newtons. And we have this angle to be 90 degrees. So this is already the perpendicular component. So this is going to be 7.5 newtons meter. And it's going to be positive. This force, if you just look at that force and ignore F2, this force is going to try to rotate your object counterclockwise. So that's going to be a positive torque. Now, tau 2, we're going to have 0.25 centimeters, or 0.25 meters, times the force that is going to be 20. And that's going to give me 5 newtons meter. Now, in this case, if I just look at that force, this force is rotating the object clockwise. So that's going to be a negative torque. So this is going to be negative 5.0 newtons meters. So this is clockwise. And this is counterclockwise. Okay. So the net torque is tau 1 plus tau 2. This will be 2.5 newtons meter. So this thing will be rotating counterclockwise. So this will be rotating like this. Okay. Make sense? Okay. Last problem. It's pretty similar, same object. We still have the pivot at 1/4. And now we have the same forces. What was it? 10 newtons? But now this angle is going to be 30 degrees. And then we have the other force, 20 newtons, and this angle is going to be 20 degrees. Again, we want to calculate what is the net torque. So now you need to calculate that perpendicular component and be careful with the angles. Don't think it's always going to be exact by.
Yes. So I have to do this twice. Okay.
Well, remember, you need to calculate the perpendicular component.
Yeah, I guess we don't have to do that, this is what happened in the last problem, because this is just like 1, 2.
So same thing, you have 90 angles, so this, the sine phi will be sine of 90, which is 1.
Here,
But be careful, one is the angle with respect to the irregular, and the other is the angle with respect to the
Yep.
So this is cosine. So if I just look at, I'm just going to be looking at this. So I have this force here. And this is 30 degrees. So if I do cosine, I'm going to be calculating this. And this component is parallel to the radial line. So that is not going to create any torque. You need the perpendicular. So in this case, it's be careful with the angle. Yeah,
Oh, you drew it, okay.
I can draw it different. Okay, so really quick, remember what we want are the perpendicular components of each force. So I'm gonna look at what we call that one. This is gonna be F1, and this is gonna be F2. So if I look at F1, this is gonna be my parallel and perpendicular axis, and I want the component that is going to be perpendicular on the perpendicular axis. Okay, so tau 1 is going to be the distance, 175, and the perpendicular component is going to be F1 sine of 30. Okay, so this is going to be 0.75 times 10 sine of 30. And that's going to be 3.75 newtons